Now let's go to our final speaker of today, which is Lorenzo Catani. Lorenzo did his PhD in 2018 at University College London. He's been a postdoc at Chapman University in California, and now he's a postdoctoral researcher at TU Berlin. And he will tell us about why interference phenomena do not capture the essence of quantum theory.
Yeah, thanks for the introduction, and thanks for inviting me. I've been enjoying this a lot. So today I'm going to talk about this project I developed with Matt Liffer, David Schmidt, Rob Speckens. You can find more about it in the archive. And so I'm going to talk today about what is the essence of quantum theory, in particular in the context of interference phenomena that, you know, are usually considered to be one of the most characteristic features of quantum theory. And I think that the topic of this talk fits with the theme of the conference, because I think it's quite important to understand what is the conceptual innovation of quantum theory with respect to classical theory, in particular if you want to understand if and to what extent you need to abandon the materialistic classical worldview. Moreover, let me say that I think it's quite important to have this classical, non-classical boundary, at least in quantum theory, because, you know, in quantum foundation, often we hear or we come up with interpretations or claims that are quite radical. But, you know, the reason why they're so radical sometimes is because we don't understand very well which features of quantum theory really constitute a departure from classical explanations. And so sometimes we are too radical. Ultimately, I think that, you know, the right interpretation of the quantum formalism is going to be one where we are radical only where we need to be. So in this sense, I really advocate for an interpretation of a view where we're the least ontologically expensive, let's say. So having said that, I'm not going to talk much about the novel, the conceptual novelties of quantum theory in this talk. We can talk about it later in the discussion. I'm going to talk mostly about some features of quantum theory that usually people say that really capture the mystery of the theory. Actually, here I'm going to show that they are not. And so this brings me to the, you know, telling you what are the chapters of the story I'm going to tell you about today. So I'm going to start with some extra motivation, and in particular, I'm going to introduce the standard way of describing quantum interference, which is through the Feynman's two-slit experiment. Then I'm going to move to an even simpler way of defining quantum interference, which is in the setup of Mach-Zehnder interferometers. And let me say that if there are listeners that are not physicists, I mean, don't be scared by this. I'm going to be very pedagogical. I've removed any equation. But the whole point of this first part is going to really be to reproduce the aspects of the phenomenology of quantum interference that are traditionally regarded as problematic. And with that, I mean those aspects that usually are associated with interpretational claims that depict quantum interference as inherently mysterious and capturing the essence of quantum theory. In the second part of the talk, I'm going to introduce the toy field theory, which is an alternative theory to quantum theory that reproduces this phenomenology, but explicitly rejects all these interpretational claims. So it's going to provide a classical account of this basic phenomenology of quantum interference. At the very end, I'm going to spend a few words on which more nuanced aspects of the interference phenomenology actually capture a departure from the classical worldview. So with this in mind, let me start with the two-slit experiment. And literally here, I'm going to use the narrative of the Feynman lectures of physics. And let us start by considering something that is not quantum at all, but some very materialistic objects like bullets. And imagine that we have like a bullet gun that shoots bullets towards a wall, which is pierced by two slits, 1 and 2, and then let us imagine that we have a backstop at the end. And the goal here is to, you know, collect the distribution of these bullets. If you run this experiment, what you're gonna notice is that the distribution at the end is this one. It's like a bell-shaped distribution, okay? And this can just be imagined as being given by the sum of the distributions is if slit 1 is closed or if slit 2 is closed. And as a matter of fact, in this kind of context, you know, this distribution really tells us that the input system is particle-like. You know, it's like a material object with the properties that are position and momentum. So let us see what happens instead if we put a wave source. For example, imagine you have a water wave, same experiment. This time, what you're going to obtain as the output distribution is this interference pattern. And you see, this is quite different from the one before. And indeed, it's not given by the sum of these two probabilities that I would have if I just close one or the other slit. And as a matter of fact, this interference pattern really tells us that the input system is a wave. And you know, waves and particles are quite different. A wave, the essence of a wave is to have an amplitude for every point on space. Like here, the role of position is not dynamical as before, but is really to index the space. So you see in this two-slit experiment, like interference pattern denotes waves and the bell-shaped distribution denotes particles. So let us see now what happens if we put our beloved quantum system, like for example, an electron. Imagine you have this electron gun, so you run this experiment many times, you shoot these electrons. This time what happens, you know, surprisingly enough, is that you obtain an interference pattern. So it seems that, you know, like you might conclude from this that, you know, actually, you know, like an electron, a quantum system, in essence, is like a wave, is like a water wave. But then at this point, you might ask, I mean, look, this might sound a bit strange, you know, like a wave, you know, is simultaneously present at both slit 1 and 2. I mean, what does this mean, this concept for an electron? And so you might ask, oh, let me actually investigate at every run of the experiment, where does the electron passes through, which slit? So if we try to do that, and so we place a which-way detector, for example, a light source close to one of the two slits, what you obtain, and this seems very puzzling, is that now the electron starts to behave as a particle. So we obtain a bell-shaped distribution. So this sounds very puzzling. I mean, what is an electron? Is it a wave or is it a particle? And the thing seems even more mysterious because it seems that if the electron behaves as a wave or as a particle, really depends on the observer, on if we decide to place the light source, the detector, or not. Moreover, it also seems impossible to have a local explanation of what's going on. Imagine the case where the electron goes in the slit 1. How can the electron know if there is or not in the other slit a detector? Because if there is a detector, then the electron is going to give us this bell-shaped distribution. But if there is not, then it's going to give us the interference pattern. So it seems that there must be some instantaneous, spooky action at a distance between the two slits. So all of this really seems to depict a very, you know, mysterious story. And this sentiment was quite eloquently stated by Feynman in introducing, you know, these two-slit experiments at the beginning of its third book of the Feynman Lectures of Physics, where he says that this is a phenomenon which is impossible, absolutely impossible to explain in any classical way. It contains the only mystery. In telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics. So all of this seems very compelling, but what I'm going to show in this talk that this is incorrect. In particular, we're going to dispute the widespread claims that the basic phenomenology of quantum interference resists explanation in terms of a classical worldview. And really, the first question to ask at this point is to try to be more precise on what we should consider to be mysterious about quantum interference. Can we distill what is, you know, assumed to be mysterious about quantum interference? And I'm going to answer this by moving to an even simpler scenario than the two-slit experiment. In particular, this is the setup of Mach-Zehnder interferometers. So what is a Mach-Zehnder interferometer? Okay, the Mach-Zehnder interferometer is this optical experimental apparatus where you imagine that you have a light beam, so our photon gun, let's say, and this impinges a 50-50 beam splitter, which is just an optical device that 50-50 splits the beam into a reflected and a transmitted beam. On the right arm, we assume that we have a phase shifter that is going to change the phase of this beam, and we assume that the phase shifts can only be given by 0 or pi phase shifts. Then we have two mirrors, so nothing really happens. We just recombine the two paths in a second 50-50 beam splitter. And then at the end, we have the two output ports, left and right port. Let me say that this is one configuration of the Mach-Zehnder interferometer we're going to consider. And the other configuration is one where instead of the phase shifter, we place a which-way detector that is going to detect whether there is a photon or not in that arm. Let me stress that we're going to consider just these two very simple configurations with 50-50 beam splitter and 0 pi phase shifter, just because these are enough to reproduce the phenomenology of quantum interference that is traditionally regarded as problematic. We don't need to consider more complex scenarios. But let us see what is this phenomenology in question. Okay, so let us start with the case where we have the Mach-Zehnder interferometer with a 0 phase shift. So basically there is no shift here. What happens in this case, if you run this experiment many times, is that every time you're gonna see the photon outputting on the left output port. I'm not gonna give the quantum mechanical description, but in there it's very simple, because what you're gonna see is that the unitary associated to the beam splitter cancel out. And so if you start with the left arm being occupied, you're gonna get that the left output port is gonna fire. The other situation is where instead of we actually put a phase shifter, so a pi phase shift, the action of this is gonna be that now the contribution to the left output port is gonna be 0, and instead we're gonna see every time the right port to fire, okay? And let me say that both these two cases with the phase shifter correspond to the cases of wave-like behavior that we saw before with the water wave in the two-slit experiment, or with the electron without a which-way detector. And the reason how you see it here is that if you want, this is like a two-slit experiment, but where you only have two possible paths, and where the screen at the end, or the absorber, is just made by 2 points, okay, not by a continuum of points. Like the 2 ports are just the only 2 possible, outputs for the photon, for the particle. And so you see that what we experience in this case with phase shifter is really an interference pattern, because we find a maximum of probability of detection in a port and a minimum of the other, and we can toggle between the two by changing the phase. So it's really an interference pattern. From this, one may really think that the photon does behave as a wave. The other configuration is one where we place a which-way detector, and let us imagine the case where the detector here does not detect the photon. So this means that the photon passes through the other path. And then, by the way the beam splitter works, we're going to have that 50% of the time the left output port is going to fire, and 50% of the time the right output port is going to fire. As you see in this case, we have a uniform probability distribution over the 2 ports. There is no interference, and this is like the particle-like behavior of the bullets or of the electron when we place the which-way detector, okay? So we see that also in this Mach-Zehnder interferometer, in an even simpler way, we can reproduce this basic phenomenology of interference. And in particular, I'm gonna call this basic phenomenology of interference as the phenomenology of interference that is traditionally regarded as problematic, or trap phenomenology as acronym, because with this we want to say that this is considered to be surprising, but this is a trap. It's not really the case. But let us really see why it is usually considered to be surprising. So let me actually list and point out which are all these interpretational claims that are usually associated with this trap phenomenology. So the first one is this wave-particle complementarity. So it seems that the quantum system, like the photon, sometimes is a wave, sometimes it's a particle, and it's like this dualistic kind of entity where there is no possibility of a unifying description. And we have seen that waves and particles are two really different things in classical physics. So it really seems to be a notion of non-classicality, this wave-particle complementarity. Moreover, it seems that if the photon is a wave or is a particle, does depend on what the observer decides to measure. In particular, we saw that if we put this which-way detector, then the photon behaves as a particle. Otherwise, it behaves as a wave. Finally, it seems impossible to provide an explanation in terms of local causes. Again, imagine the case where there is the photon who is in the left arm of the Mach-Zehnder interferometer before the second 50-50 beam splitter. Then in that case, it seems that the photon must know whether there is a detector in the other arm or not. Because if there is no detector, then the photon is always going to output on the left. But if there is a detector, then sometimes it can output on the right. So it seems that there must be some non-local causal influence from one arm to the other. And so by describing this, what I've done so far is really just to tell you what is the trap phenomenology of quantum interference and what are the interpretational claims associated with it. Wave particle complementarity, observer dependence on reality, failure of explanation in terms of local causes. At this point, I'm going to introduce the toy field theory, which is an alternative theory to quantum theory, is a version of the well-known Speck-and-Stoy theory. And this theory is gonna reproduce the phenomenology, the trap phenomenology of quantum interference, while explicitly rejecting all these interpretational claims. Let me say that I'm not gonna define the theory in details. I'm just gonna provide you what is the theory construction scheme to define it, and then gonna just put it in action. I'm gonna just show you for the phenomenology under examination how it works. Okay, so the toy field theory. The toy field theory is an example of what is called a classical statistical theory with epistemic restriction. So what does this mean? It means that in order to define it, we need to specify three things. So the first one is what is the classical underlying physical theory. This means to specify what is the kinematics and the dynamics of the theory. So the kinematics means to specify what are the systems of interest in this theory. In particular, in the toy field theory, the systems are two field modes, the left and the right mode. So let me say that this is quite common in the, in physics, talking about fields that are just associated with these regions of space where we associate a physical quantity to every point. And in particular, in this field picture, the systems are these field modes that are like, motion patterns. Like in the electromagnetic field, this would be like the patterns of the propagating waves, okay? And so it's nothing, there is nothing radical about that. The only different thing here is that these fields are discrete. So really the system are these two field modes, the left and right mode of the Mach-Zehnder interferometer. And what are the properties of these field modes? Each mode has an occupation number and a phase, and these are specified simultaneously at every time. In particular, we're going to denote this with n for the occupation number and with phi for the phase, for the left and right mode. They take values 0, 1, only these two. And we also assume that at every time, only one of the two modes is occupied. And we say this by saying that the sum of the occupation number is 1, or also the difference, given that the arithmetic is modulo 2. The dynamics here, I'm not going to go into the details, but you're going to see it in action in a bit, is going to be fully deterministic and local. And so you see at this time, by defining, kinematics and dynamics, what I did is really just to define a classical theory. This is like in classical Hamiltonian mechanics, when you define your elements of reality, your system as being, particles with a position and momentum, and evolution is the one governed by the Hamiltonian equations. Now, the other thing we're going to consider is a statistical theory associated with this classical physical theory, because we want to also be able to talk about the possibility of being uncertain about what are the properties of this system. And so we want to associate probability distributions with these properties. So this step is like when you build what is called the Liouville classical mechanics on top of Hamiltonian mechanics. And you see so far, point 1 and 2 are really just like classical physics, but over discrete fields. The last ingredient is that we assume that not all the probability distributions are allowed in this theory. There is what is called an epistemic restriction. It's called this way because if you interpret probability distributions as state of knowledge, this restriction really says that there is a constraint on how much you can know about the properties of the system. In particular, in this toy field theory, the epistemic restriction says that for a single mode, no agent can have knowledge about more than one property. So if you know the occupation number, you are completely ignorant about the phase and vice versa, or you could know the sum of these two variables, but you would be completely ignorant about the rest. And then there is also an epistemic restriction for when you have a couple of modes and so on. But so like in summary, the toy field theory is a classical statistical theory over two field modes with an epistemic restriction, okay? Let us see now it in action, how it reproduces the trap phenomenology of quantum interference. So you remember the first stage in the Mach-Zehnder interferometer was that we had, our, beam coming from the left. And in this case, the toy field theory associated with this stage the state of knowledge where we know that the left mode is occupied, the right mode is not, and so because of the epistemic restriction, we are completely ignorant about the values of the phases. How do we represent the beam splitter? Well, the beam splitter is simply associated with what is called the swap rule in the toy field theory. This rule just says that every time you need to represent a beam splitter, the way this acts is by swapping the value of the occupation number of the left mode with the relative phase between the two modes, while keeping all the other values constant. Let us see this in action, as it might seem a bit abstract. So this was, you remember, the first stage of the Mach-Zehnder interferometer. So the initial state is the state of knowledge where we know that the left mode is occupied, the right is not, and we are completely ignorant about the rest. We apply the swap rule corresponding to the beam splitter, which means that the value of the occupation number of the left becomes the value of the relative phase. And so this is actually exactly what we do. We end up in the state of knowledge where we know that only one of the two modes is occupied, and then they are anti-correlated. So the sum or difference of their phases is 1. But of course, we are completely ignorant about the individual values of all these variables, okay? So now, just as a notation matter, let me call this kind of state where we know that the occupation number of the left mode is left, as saying that is the state with NL is equal 1. And let me call this state where we know that the relative phase is 1 as the state that has relative phase 1. This is just a notational matter in order to soften the notation. Because now we are ready to actually reproduce the configurations of the Mach-Zehnder that I told you before that define the trap phenomenology of quantum interference. So let us start. So at the beginning, we already said, like, we have the state of knowledge where we know that the occupation number of left mode is 1. We apply the swap rule in correspondence of the 50-50 beam splitter. We go to the state where we know that the relative phase is 1. We assume now that there is no phase shift, so nothing really happens. We arrive to the second beam splitter, swap rule again, so this becomes the value of the occupation number of the left mode, which means nothing but that the left output port is always gonna fire, which is exactly the phenomenology of the Mach-Zehnder interferometer in this case, wave-like behavior. Let us see the case where we place a pi phase shifter. So at the beginning, same story, swap rule. Now, the action of the pi phase shifter is going to be to flip the value of the local phase of the right mode. And as a consequence, this is also going to flip the value of the relative phase. So we go from having anti-correlated modes to having correlated modes. Now we apply the swap rule, and now the value that the occupation number of the left mode acquires is 0 and not 1. And this means that every time we run this experiment, it's going to be the right output port to fire. So again, we reproduce this wave-like behavior also in this case. Now let us see the case where we place a which-way detector in the Mach-Zehnder interferometer. In order to tell you how the toy field theory reproduces this case, I need to tell you what is the measurement update rule in the toy field theory, in particular in this case when we want to perform a measurement of the occupation number. So the measurement update rule is made of two parts, 2 steps. So the first step is the learning step. So we perform the measurement of the occupation number and we get the knowledge of what is the value of the occupation number of that mode. So we assign 0 probability to the physical states that are inconsistent with the outcome. And then we have also an extra step, which is a disturbance step, where we also need to randomize the local phase of that mode. And you can imagine this randomization as doing half of the time a flip to this local phase and half of the time to leave it unchanged. Of course, we need this disturbance step because if we didn't have it, we would violate the epistemic restriction, right? If we knew the value of the occupation number and we already knew the value of the phase, then we would know the property of the state, but this is not allowed in the toy field theory. So we also need this disturbance step as a consequence of the epistemic restriction. So let us see this measurement update rule in action. Again, we want to reproduce the phenomenology of this Mach-Zehnder interferometer. So we start as usual. We know that the occupation number of the left mode is 1. We apply the swap rule. It says that our modes are anti-correlated. Now we post-select on the case that the detector measures occupation number on R, and let us assume that it doesn't detect the occupation number there. So as a consequence, if we apply the measurement update rule, we get to know that the occupation number of left mode is 1, the one of right mode is 0, and we are completely ignorant about the phases, okay? Now we can apply again the swap rule, and the final state is going to be the state where we know that the modes are anti-correlated, but we know nothing about the value of the occupation numbers. In other words, this says that every time we run this experiment, we're going to obtain 50% of the time the left port to fire and 50% of the time the right port to fire, which is nothing but the particle-like behavior we saw before. So at this point, we just saw that the toy field theory reproduces the trap phenomenology of quantum interference. And let me really quickly summarize how it does it. If you realize what is the output port that is going to fire, always depends on what is the value of the relative phase before the second 50-50 beam splitter. In the case of wave-like behaviors, this value is always fixed because it comes from the swap rule of the initial state in the toy theory. In the case where we have a which-way detector, this locally acts on the phase of the right mode, it randomizes it. As a consequence, also the relative phase is randomized, and so we don't know which port is going to fire, and this is the particle-like behavior. So the interesting thing is that the toy theory reproduces this phenomenology in this quite simple way, and at the same time it rejects all the interpretational claims I listed at the beginning. Let us see them one by one. Wave-particle complementary. You remember the story that the quantum system seemed to be this dualistic kind of entity toggling between being a wave and a particle. Here the system is always two field modes. It never changes the nature of the system. The variability concerns what we know about the properties, occupation number, and phase of the system. So no wave-particle complementarity. Observer dependence on reality. It seems that the quantum system is a wave or is a particle depending on what we choose to measure. Again, here, the system is always two field modes with well-defined properties, occupation number, and phase at every time. And what is observer dependent here is what the observer decides to know about this property, not about the reality itself. Finally, we had this failure of explanation in terms of local causes. Well, all the dynamics in the toy field theory is explicitly local. In particular, you remember the problematic case was when we had this which-way detector, but the way we model the which-way detector in the toy field theory is that it causes a disturbance in the local phase, so half of the time it flips it, half of the time it leaves it unchanged, and then this information propagates to the second beam splitter. We get to know that the relative phase also is randomized, and as a consequence, we explain why also 50% of the time we obtain left output port firing and the other half of the time the right output port firing. And you see, like what was thought to be no local causal influence, here is just if inference. It's just update of knowledge. And notice how important is that the unoccupied mode, what would correspond in quantum theory to the quantum vacuum state, here is just a valid state of knowledge as any other. And as such, it can carry information. In particular, it carries information about the local phase. So also failure of explanation in terms of local causes goes. So in summary, the toy field theory reproduces the trap phenomenology of quantum interference while rejecting all the interpretational claims usually associated with it. We can run similar analysis also for related experiments like Elliott-Subweiman bomb tester, Wheeler delayed choice experiments, quantum eraser. You can find it. You can find about it in the paper. And let me conclude by saying that so the trap phenomenology of quantum interference does not capture the essence of quantum theory. This mere phenomenology does not force us to accept the interpretational claims that I listed before, and we have provided a classical statistical theory that can reproduce this phenomenology. And I think that there is a lesson associated with this result, which is that if you want to do research on the non-classicalities of quantum theory, it's not enough to identify a feature that seems impossible to explain in any classical way, even if you tried hard, even if you are very smart. but you should back up these claims with rigorous no-go theorems, where you formally establish a notion of classicality and you prove a contradiction with the phenomenology under examination. And the successful attempts of doing that are like Bell's theorem, Conkes-Specker theorem, and even more recent no-go theorems. And you see, like, there is still a project to undertake here for quantum interference according to this methodology, because so far we just showed that the trap phenomenology of quantum interference accounts for a classical explanation, but maybe there are more nuanced aspects of the interference phenomenology that actually can witness non-classicality. And so my very last slide is going to be about advertising this follow-up work that actually is going to be out in the archive on Monday, where we show one aspect of interference phenomenology that actually defies any classical explanation. And this is the functional form of what are called wave-particle duality relations. In particular, we show that the functional form of wave-particle duality relation can witness non-classicality in the form of contextuality, where contextuality is one of the leading notions of non-classicality. In particular, this work is based on this other work that I cited here. And let me just say that wave-particle duality relations are a quantitative way of describing quantum interference. Basically, they are trade-off relations between a wave-like property, which is the fringe visibility, and a particle-like property, which is the which-way distinguishability. And what we show is that the quantum trade-off between visibility and distinguishability that follows this quadratic rule, and here is drawn in blue, actually exceeds what you can achieve in any classical, or in this case, non-contextual model. Because in any non-contextual model, the trade-off between visibility and distinguishability is bounded by this linear bound, okay? So really, the lesson is that the mere existence of wave-particle duality relations is not enough to have a proof of non-classicality. Even the trap phenomenology before had it, and even the toy field theory can account for it. But if you exceed, is the functional form of the trade-off that really witness non-classicality. So ultimately, if you go to the lab, you want to run your interferometric experiment, modulus some extra symmetry assumption I haven't talked about. What you have to do is you have to evaluate your fringe visibility, you have to evaluate your distinguishability, and if they give you a trade-off that exceeds this linear non-contextual bound, then you're really witnessing non-classicality, so a departure, if you want, from the classical materialistic worldview in the context of interference phenomena. Thanks for your attention.
Thanks for the very nice talk. We have perhaps 5 minutes for questions and discussion. So among the speakers, is there anyone among maybe Emily or Daniele? Well, Jacques is already gone, I think. He may come back, so he had to leave for a bit, unfortunately. So it's only the three of you now. Okay, so anyone wants to comment? Emily.
Yeah, thanks for this talk. I guess I wondered, the de Broglie-Bohm interpretation gives a fairly classical account of the two-slit experiment. I wondered if you could say sort of how this approach differs from that one.
Yeah, so I mean, the main point is that while the main difference is that in the Bohmian interpretation, basically the ontology is to have both a particle and a wave. Like instead here we have two field modes, which is a different ontology. And then the main crucial difference that the Bohmian theory cannot account locally for the quantum eraser, while the toy field theory can. So that's, I think, the main important difference. So it seems like that the Bohmian mechanics can only do this very simple scenario, but not the more complex ones.
Right.
So maybe I can pose a quick question now. So for people who haven't heard of this before, it sometimes sounds a bit perhaps suspicious or implausible to say, let's assume this epistemic restriction. It seems like something you put in by hand, which is not directly justified. it certainly does its job, and that's why I like it. So it's not a criticism I would put out, but probably something you hear very often. So you can reproduce now the phenomenology by classical means, but have you thought, for example, of, or is there actually work, maybe by Rob actually, that justifies this epistemic restriction to begin with? Or maybe a story you can tell about the detection device in one of the arms. You would say you kind of naturally expect it to disturb the particle 50-50.
I mean, I don't know which kind of work is done in this direction, but the way I like to put it is that, so let us imagine that, I don't know, for some reason, the toy field theory, for example, could explain everything, you know, about quantum theory. Then one would say, okay, maybe this is like really a good interpretation of the quantum formalism. What would be the things that would need to be done in this interpretation now to, you know, solve any possible problems? And one would be exactly to try to justify why the epistemic restriction. And I think one could come up with some mechanism, like either from thermodynamic reasonings or by some reasoning similar to, I think, the Heisenberg microscope. So actually, even classically, when you perform a measurement like the unavoidable disturbance that are going to go into that, and try to justify why this actually leads to the epistemic restriction, or this very symmetric one, how it is here. The point of the toy field theory is really to show that some things that are usually considered to be very mysterious actually are not, because they can be done in this very simple model. And I mean, I think given that that is the main motivation for doing that, I'm not sure there is much motivation to really, I don't know, really explain any interpretational issues as if the toy field theory actually is the theory of the world. But yeah.
Yes. I mean, maybe you don't need to come up with such a justification, because maybe just before I go to Daniele, a little follow-up here, because maybe you can now say, well, look, whenever I have an interferometer of that kind and I only have 0 or pi phase shifts, then I can learn from that I cannot use that setup for any tasks, to do tasks better than I could do classically. Like metrological improvement that I couldn't also have classically, or some other kind of thing. So that this relates a bit to the idea that this provable notion of non-classicality, like contextuality, often comes with resource improvements like computational speedups or so. And this is something you can probably now exclude for that specific setup.
Yeah.
Would you agree? Yeah.
So let me also add to this that the way this model is classical, maybe I didn't go into that also because I want to try to deliver, you know, like a presentation that could be understandable to anybody, but it's quite formal the way this model is classical, you know. Particular, our notion of classicality is one where we have, you know, the kinematics is made of sets, the dynamics is made of functions, and we obey this principle of no fine-tuning or Leibnizianity or generalized non-contextuality, if you want. So it's classical in a very precise sense. Of course, this is a more permissive notion of classicality than just, you know, being just classical Hamiltonian mechanics, for example. And of course, it allows you to have more resources. But the good point you made is that there are many results now connecting the computational power of, you know, the computational non-power of non-contextual models, and how contextuality is a resource for performing better information processing tasks.
Yeah. Well, thank you. So Daniele, I think you have raised your hand.
Yeah, it's half a comment, half a question. And it's in the same line of what Markus was saying. So the way I understand your result is showing that quantum mechanics can be understood as an effective way of dealing with epistemic restrictions, while it may not be incompatible with you know, a strong realist attitude towards you know there is a system out there with certain properties and you know, a certain set of equations governing the dynamics. But I wouldn't really say that it shows that somehow the interference is not a puzzling phenomenon, because what normally one understands by that, at least what I normally understand by that statement, is that it cannot be understood within classical mechanics, which includes the absence of such epistemic restrictions. So for me, when I understand quantum mechanics as a theory of the world, it comes with the statement that, you know, there is a list of properties, there is a set of equations, and at least in principle, all of that is accessible. There's nothing else that is going to limit my access. But to some extent, that is not really relevant. It's extremely important that you can show, you know, to what extent there exists a classical looking model that reproduces the phenomenon, and how much you can instead shift to the level of epistemic restrictions of the usual quantum puzzles. So the importance of the result remains exactly the same. It's just that I think that the absence of epistemic restrictions is part of what we normally would call classical mechanics.
Yeah, let me comment on that, I think it's not particularly interesting to have a notion of classicality that is so restrictive as to say that it needs to be present in classical Hamiltonian mechanics. I think a notion of classicality is compelling if it's more permissive, like in this case, the notion of non-contextuality that also allows to have this kind of models. And let me revert your comment by saying the following. Imagine that we lived in a world governed by the toy field theory, okay? In that world, we would still have a quantum interference, how you want to call it, okay? But it wouldn't constitute an interpretational problem. Instead, what still constitutes an interpretational problem in quantum theory are not like the simple quantum interference like here, but are like Bell inequality violations, non-contextuality violations. Those are the serious things that are non-classical and mysterious about quantum theory. That's where we should put our attention. So I think that's the value of this result. It tells you what is strongly non-classical.
So I certainly agree with that, that, you know, Bell's inequalities and so on will pose a greater challenge. But I would say that in exactly the world you're mentioning, you're suggesting, an issue would be to explain the origin of the epistemic restriction, which is what Markus was asking. So that's the sense in which I would say that even interference in that world will come with a challenge.
Yeah, I agree with that. I just think it's a way weaker challenge than explaining Bell's theorem. I agree.
Okay, great. So yeah, let's thank Lorenzo again for the nice talk.